Hello and welcome to News in Statics. In this video, we shall give a brief mathematical basis of the fact that diversification of your financial investments reduces the volatility of return. In other words, if you invest in more than one instrument, then definitely the volatility, or what is known as variance in statistical terms, on your return decreases. So you decrease the risk factor. So before going into the explanation of that, let's revise some basic concepts of variance. So we can always write that the variance of x is the expected value of x minus mu x whole squared. And if we expand this, we will be also able to write this thing as the expected value of x squared minus mu x squared. Another important concept is that if I replace x with if I replace x with x plus c, okay, then both x and mu x are translated by a factor of c. So the difference of x and mu x is still unaffected. So the variance of x plus c is equal to the variance of x. And if I replace x with kx, then both x and mu x is translated by a factor of k, and when it comes out of it, it becomes k squared. So the variance of kx is k squared times the variance of x. Using these concepts, let's find the variance of x plus y. Now let's assume that this x plus y is equal to z. Okay, so essentially it's finding the variance of z, which is equal to the expected value of z squared minus mu z whole squared, which I can write as the expected value of x plus y squared minus mu x plus mu y whole squared. Now if you do some algebraic simplification, what you'll get is the expected value of x squared minus mu x squared, which is nothing but the variance of x, and then you also get the variance of y, and you'll get a term which is twice the expected value of xy minus the expected value of x times the expected value of y. And this thing is known as the covariance, twice the covariance of x and y, which is 0 if x and y are independent. So I'll assume the case where x and y are independent, and therefore as you can very well understand, that the variance of z will be equal to the variance of x plus the variance of y if x and y are independent. So let's assume that we have 1 rupee. Let's assume that we have 1 rupee, and we want to invest a fraction a of this rupee in an instrument which has a return of x, and we want to invest the fraction 1 minus a of this rupee in an instrument which has a return of y. So my expected value of return in such a situation will definitely be equal to a times x plus 1 minus a times y. And all of these are random variables, by the way. My variance of r, which I can also write as say vr, will be equal to a squared times the variance of x plus 1 minus a squared times the variance of y. Because why does it become square? I've already discussed. So now I have this very important equation. I differentiate this equation with respect to a, and I get that on the right hand side 2a vx minus 2 of 1 minus a vy equal to 0. Now if I do the second derivative, I'll find it to be positive, and therefore it's a minima. And this minimum will occur when this thing becomes equal to 0. That is, when A is equal to Vy upon Vx plus Vy. What I'm trying to say is that if you plot a graph where A is on the x-axis and the expected value of R is on the y-axis, then you will find a minima point where the expected value where the variance of R is on the y-axis, where the variance of R assumes a minimum value at a certain value of A. So if you can optimally choose your value of A, you can reduce the variance on your return to a theoretical minimum. Now in this case, if Vy and Vx both are equal to each other, then it would be like V upon V plus V, which is equal to 0.5. So if you invest more or less equal amount of money in both X and Y, then you reduce your variance to a theoretical minima. And if you invest in more than two instruments, a similar mathematical logic holds good. So this was a very brief explanation about the fact that diversification of your investments indeed reduces the variance on your returns. Well, on another day with another topic, and until then, bye-bye.